All right, let's go, team. So, thermochemistry, kids. Today, our notes. Kids, young adults, almost grown-ups, near voting age, voters, potential voters, soon-to-be voters. Okay, I'm done. All right, notes for my thermo kids. Organic people. Or I can open up S5. Because you guys clearly want to talk to each other. You're clearly trying to talk to each other. And I needed a lot quieter. All right. My goodness, I cannot start these notes. Everybody wants something. It's taking us, I don't know how long. What's the date? The 14th or 4th. Okay, I think we're getting closer now. Are we ready? Why are you looking at me? I'm giving notes right now. Go find something else to work on. This is the problem when you guys are trying to do too many things. Okay. All right. How much time of dead time? Okay, there's like 2 minutes. So when you guys watch this video later, skip ahead 2 minutes because that's just us waffling around. Okay. Ready? Notes. Okay. So what we are talking about today is polarity. When we are discussing what polarity is, we are talking about the overall charge of a molecule. Polarity. The overall charge of a molecule. We have two choices when we are thinking about polarity. You either have something that's nonpolar or bipolar, no. Nonpolar and polar, those are the two choices. So a nonpolar molecule is something that has no charge. And a polar molecule has a slight negative and a slight positive end. Did I spell slight right? I did. Let me draw you a water molecule because the water molecule is a good example of something that's polar. So if I have a water molecule, I would have an atom of oxygen and I would have 2 hydrogen atoms attached to it in a covalent bond. One side of my molecule is going to be slightly negative. That little kind of fancy looking D is, I want to say delta in the Greek alphabet, and it just means slightly. So it's not fully negative. It's not like a negatively charged ion. It's just slightly negative. The hydrogen end is going to be slightly positive. So I'm just trying to indicate with the molecule what's negative and what's positive. And then remember, it's only a slight charge. It's not a fully charged ion kind of thing. Are we okay so far? Yes or no? Okay. I'm looking at Klein and he looks panicked already. That's concerning. All right, keep going. Is there something you want me to backtrack on, Klein? No? Okay. So When I'm trying to decide whether or not my molecule is going to be polar, there's a couple of steps I need to do for that. The first step that I need to ask is, are the molecules sharing those covalent electrons evenly? Actually, I should say, is the molecule. Say covalently bonded electrons evenly. If my answer is yes, then what I have is a nonpolar covalent bond. Now, unfortunately, we are going to be talking about polar and nonpolar in two different contexts. We're going to talk about it in the context of the overall molecule and in the context of the bond. It's really important that you distinguish the two, because otherwise it can get very confusing. So that's why I'm saying bond here. If the answer is no, then I have a polar covalent bond. Now, the way I decide this is based on the electron negativity. Oops, now I'm running out of space. Actually, I don't know if it's one word or two words. I think it's two words. It is two words. So this is based on electron negativity. We did this in thermochemistry. So if you guys remember, sorry, thermochemistry, we're doing thermochemistry right now. We did this in the periodic table trends. If you guys remember, I gave you a periodic table with all the numbers of the electronegativities for the different elements. And with electronegativity, we are talking about what is the attraction between the nucleus and those valence electrons. Does it have a really strong attraction to it, or does it not? When we are doing a covalent bond, those electrons are being shared. Actually, let me backtrack. So we know what electronegativity is, right? Do you need me to write down the definition, or are we okay? Sorry, let me backtrack. Do you guys need me to write down the definition for electronegativity? Yes? Okay. So electronegativity is referring to the attraction between the nucleus and the valence electrons. So FYI, we did this in periodic table trends. All right. So when you guys are looking at the various numbers for the electronegativities, we can do a subtraction between the electronegativities between the different elements and basically get a difference. So if my difference in my electronegativity between those two elements are between 0 and 0.4, those electrons are going to be shared relatively equally. So this is going to be a non-polar bond. And that's referring to the difference in electron negativity between the atoms in the covalent bond. Or sorry, I should say in the bond. So if my difference between those two elements is somewhere between 0 and 0.4, that would be a nonpolar bond. If that difference is between 0.4 and 2, then I would have a polar covalent bond. Like if I looked at the periodic table and was checking the electronegativity differences. Grab one of those actually. Here we go. So, find an example. So, for example, now I'm trying to find one. There's a small enough difference. Pretty big differences. All right. So, if, say, for example, I have boron bonded to a hydrogen, and I did the subtraction of 2.1 minus 2, I would get 0.1. So the bond between the boron and the hydrogen is going to be a nonpolar bond because it doesn't have a huge electron negativity difference. So the electrons are going to be shared relatively evenly. If I had, for example, carbon bonded to an oxygen, that would be 3.5 minus 2.5. That's a difference of 1. So that is a larger difference. And since it's between 0.4 and 1, that will result in a polar covalent bond. Okay? If I have something that is over 2 as a difference, I then get my ionic bond. So what that means is the electron's going to get transferred. Well, so it's not going to be shared equally. Or sorry, it's not going to be shared at all. So for example, if I had sodium and chloride, we talk about sodium chloride quite often. So I'd do 3 minus 0.9, that results in 2.1. So that's a big enough electronegativity difference that the valence electron for the sodium is going to get transferred to the chlorine. So it won't even share it, it's just going to give it away. So that's ionic. Are we okay? All right. Does that make sense? Okay. So you need to think about bonds as a continuum and not as like categories per se, because it really depends on what things are being bonded together. I also want to add, they are not going to give you a table of electron negativities on the exam. Don't memorize it. It's not worth your time. I would say most of the bonds you are dealing with are going to be polar bonds, because most of the numbers when you compare against the two things is greater than 0.4. So like, for example, when I look at carbon and hydrogen, that's a 0.4 already. So don't worry about memorizing it. I would say in most cases, you're going to have a polar bond. Okay? Keep going. Yes, no? Yes, okay. I want to make sure you guys are really careful with your terminology because it can result in the difference between a merit answer and an excellence answer. Bathroom? You okay? Hey. All right. I want you guys to be really, really careful with your terminology because it will make a difference between a merit and an excellence level answer. When we are talking about things being polar and nonpolar, you're only referring to molecules. So only use the term polar / nonpolar for molecules. When it comes to ions, you will just say charged. Yeah. So I don't want you describing sodium chloride or like the sodium ion as a polar ion. It is not a polar ion. It is a positively charged ion. That's what I mean by that. Okay? Cool. The next question we have to ask when we're deciding whether or not a molecule is polar is going to be based off of the symmetry. So let's use that do now example that you guys were talking about. It was AS3 with a lone pair of electrons, and you had AS5 with no lone pairs of electrons. So I am going to be looking for AS on the periodic table and fluorine. Now, remember, again, they are not giving you guys this table. I don't want you to memorize it because 9 times out of 10, you're probably dealing with a polar bond. So that's AS, it's 2, and fluorine is 4. So that's a difference of 2. So that's going to result in a polar bond. All right. These guys luckily have the same thing attached, so that makes my life easier. So this is going to result in a polar bond, and when that polar bond occurs, those electrons are going to be closer to the fluorine atom than the AS central atom. So I'm going to draw a little arrow to show that the electrons are going in that direction. I also like to do a little cross here because what that tells me is that the AS itself is going to be slightly positive, and then the fluorines are going to be negative. Are we okay so far? Yeah, so this is going to be slightly positive when it comes to these two bonds. The fluorines are going to be negative. Do we want me to backtrack to how I figured that out? Okay, so I figured that out based off of the electron negativities. Fluorine is far more electron negative than the AS's, and so these electrons are getting pulled closer to the fluorine. And since the electrons are spending more time next to the fluorine, it's going to make it slightly negative because now it has extra electrons. Yeah. Okay. So same thing when we're dealing with this molecule over here. The fluorines are going to pull those electrons closer to it. It's going to be slightly negative. It's going to be slightly positive. So that's basically showing you how to do step 1. Yes, Manusha. Yeah. One's leaving me. What's the date? 4th. All right. Are we okay with that? All right. Next thing to keep in mind when we're looking at electron negativity is we're thinking about lone pairs of electrons because those lone pairs of electrons are also negative. Keep in mind that those lone pairs of electrons are more slightly negative than the fluorine. So I'm going to draw this as a bigger kind of slight negative. The lone pair also has regions of negativity. Yeah. So the next thing I then think about is, do I have symmetry that's going to result in the like charges canceling out? So when we are looking at this guy over here, yes, they are all negative, but they're not equally negative. This is more negative than these guys. So there's going to be no symmetry and therefore a polar molecule. Slight negative doesn't cancel. And molecule is polar. The slight negatives don't cancel. And so my molecule is polar. So in this case, I'm referring to the polarity of the molecule, not the bonds. All right. Yep. Keep going? No? Okay. Give a second. Okay. Keep going? Okay. This guy over here, all of these electron negativities, or sorry, all of these slight negatives are the same value, and so there is symmetry. So they're going to cancel each other out. And so since there is symmetry, it's going to be nonpolar. So what that tells you is that you can have a molecule with polar bonds, but a non-polar molecule. Do you want me to repeat that? Okay. I'll write it down actually too, because my level 2s were confused about this too. So if I have a non-polar molecule, it either has non-polar bonds or it has polar bonds, but the symmetry cancels it out. So those are the two instances that I would get a non-polar molecule. If I have a polar molecule, it needs to have polar bonds and no symmetry. Can I move it? No. I'm just gonna pause the recording then. Have minutes of silence. All right, I just want to show you guys the marking schedule. So this question that I actually gave you for your due now and that I've used for the notes came from the 2020 exam. And you can see the written answer here. So actually, let me show you what the question looks like on the exam. So this is the exam question. They gave you the Lewis structures and they gave you the shapes, which is really kind. And then they asked you to compare and contrast the shapes and polarities of these two things. So looking at the written answer, they're just talking about the differences in electron negativities, whether the bond is polar, and then this one is just defining the shape, looking at how many regions of electron density you have, how many are bonded and unbonded. This one has the repulsion theory about how they're separating. But like I said on Monday, the difference between last year's question and this year's question is that they are buddying up the shape and the polarity, and you're comparing both of those in one question instead of two separate questions. So some things to keep in mind for the achieve, the merit, and the excellence. For the achieve, there were two ways you could do this. You recognize the influence of the electron negativity or the number of the electron regions in the shape. So that was the achieve criteria. I have seen this in other ways where like they give you an achieve point just for guessing if a molecule is polar or non-polar. So do take a guess on the exam, even if you don't know. Your best bet is to guess that one molecule is polar and the other one is non-polar, because most likely they'll give you one of each instead of two of the same. And that's a good way just to cover your bases and try to give you an achieve point. There's lots of achieve points in thermo for just guessed answers, like guess the shape kind of answer. The merit point then was two different ways you can do it. You explain the shape and the polarity of one molecule. So they gave you two molecules and you only got one of them right. The other option was that you got both of the shape explanations. So maybe you didn't even answer anything about polarity, but you explained both shapes. Not just naming it, you have to name and explain. So the explaining is going to be this bit here about how many lone pairs of how many regions of electron density you have around the central atom, how many bonded and unbonded pairs, and then the repulsion theory. Yeah. All right, for the excellence then is that compare and contrast, and they won't give you that unless you actually compare and contrast. Oh, wow, we're running out of time. So making sure you use words like however, therefore, in contrast, both, those are things that I need for excellence. Okay? That's it.